Okay. Interesting. Hey, everybody. It is Goju. I am attempting to do a stream. This is my first live stream, and we're starting around midnight on Saturday, which is like a pretty great time to start your first stream. And it seems like we are maybe about 30 seconds behind what is actually happening in real time versus what I'm seeing on the stream. So cool. Just as an FYI. Okay. And it's giving me tips as this is popping up. So I'm going to try to figure this out. I want to make sure everybody knows I am mostly clueless about how all this works. Top chat. Okay. And I don't want to be on this screen, but I want to somehow monitor the chat. Is this, can I pop? Oh yeah, pop out the chat. Yes, that's, oh no, don't put it there. Okay. I'm gonna grab the chat here. Okay. Move this back. All right. Now I'm gonna try to, let's see, testing chat. Okay, cool. I think that works. Excellent. Cool. Thanks everybody for bearing with me while I figure this out. It looks like we've got 5 concurrent viewers. That's awesome for midnight-ish GTT on a Saturday. You need to change your video resolution. Current resolution. It doesn't like this? Huh. Why? I'm going to leave the current resolution. And if this fails, then that's okay, because I'm recording this too. And then I'll just upload my recording. Of course, there's like 1,000 things going on once. And being me, I, of course, have to do the full Goju move of, yes, we are listening to Siyoko anthology series. Excellent. Okay. So today, we are going to talk about, we're going to do a second part on Mercedes, because we're going to try to understand why I went down that rabbit hole a little bit. And then we're going to talk about this DATSA, Paranom, sysml, mlsys, uni thing. And I'm going to try to figure out what to do with all these windows. Here's what I'm going to do. I'm going to shrink this one up a little bit. I'm going to put this guy, actually I want to put this guy over here. Cool. I used to do this all the time on Nautica, except it wasn't like doing a live stream of me. It was just me with the Nautica chat, essentially. Whoa. Okay, come back. Come back, buddy. Oh, blah, 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 blah. Okay, here we go. Bring this down. This reminds me, I was watching Dave Patterson's Turing Award winning speech. This is a professor at Berkeley who is considered one of the fathers of computer architecture. Anyway, he won the Turing Award a few years back, and I've actually, coincidentally, been lucky enough to have met him in real life. So I've hung out with him a couple times. Just awesome. Super. One of my heroes. Somebody that I studied quite a bit when I was in grad school. So it was kind of like a meet your heroes moment. Anyway, when Dave Patterson was giving his acceptance speech for his Turing Award, he was having some mic troubles and the configuration, I think maybe the clicker as well. And when he finally got things working, he was like, I can win this whole Turing Award thing, and I can't figure out how to use this. So anytime I have technical issues, I kind of am reminded that other people that are far smarter than me have suffered similar types of problems and have handled it incredibly well. So my goal is to try to do the same. Okay. Now we'll leave the chat there, and we are looking at some code. I got a little distracted because I started looking at some of the notables. This one was actually, just as an aside, this is not the example I wanted to look at, but as an aside, this was kind of interesting to me because usually what Mentor does is it will, try to improve the readability. And I suspected, given this was a notable, and notables are generally they're just longer-ish expressions in the sense that it's kind of saying, did you really have to have all this stuff? Could you shorten it maybe? And so I was kind of expecting that Mentor was just going to try to do a reduction on this, a reduction of complexity, which it does down here, but it also added this check. And I thought to myself, whoa, well, that's interesting, because I didn't even think about that. I was looking at this other stuff, and then I looked down here and saw this rewrite improves robustness by including a null check for M. Ooh, excellent. And precisely verifies the return type as Boolean. Whoa. So again, I'm not an expert in Java, but, programming languages there's a lot of sort of I have this view that if you can master or get some strong familiarity, maybe, let me rephrase that. If you can maybe put in your 10,000 hours and write, let's say, maybe tens of thousands, maybe hundreds of thousands of lines of code in at least two fairly complex languages. So in this case, let's say Java would be one, and then another could be C#. If you can do this, then you're on your way to being able to become a generalist, a PL generalist. And the reason for that, in my mind, and keep in mind, I've been writing code for a long time. I think I wrote my first basic program when I was maybe 10 years old, which was 1985, so 40 years ago. And since then, I've graduated from BASIC. No disrespect to BASIC. BASIC is, it's BASIC. But actually, as an interesting factoid, my first attempt of writing Notica, this is before I actually knew how to code at all, because I was in the self-taught phase. I tried to write it in QBasic. And I was learning simultaneously. I was teaching myself QBasic and C at the time. And this was, let me try to figure out the year here. This is 1992-ish, something like this. Yeah, it's before I did my undergrad. which I think I started in 1994. So 1992, we had the internet, but not really. Like, there's no Stack Overflow. There's no... maybe Google existed, but people weren't really using it. You didn't really have browsers per se, at least not the way that we have them today. You kind of just had web crawlers. Yeah, that's more of, I think, what we had. So the takeaway is I didn't really have the internet as my resource to tell me, hey, Goju, you shouldn't try to write your large-scale software system in QBasic. That's not going to work. Although I kind of suspected that wasn't going to work. But I more just wanted to get a sense, like, at that point, I was just like, if I could just create Zork or something, I'll be happy. And I had heard about C, the C programming language, and I had purchased a few different books for QBasic and C. And I remember looking at C and being like, okay, this language there's a lot of strange characters and stuff. The syntax was a little intimidating. I since have sort of elided away any fear of syntax. That I should probably have more fear of syntax. I think maybe once you start doing like theoretical mathematics, and keep in mind my research advisor, Jeremy, I don't know if he considers himself a theoretical computer scientist. I think he probably does. But so he sort of required that I have at least a minimal understanding of theoretical computer science, where I could do like formal proofs and really high order computer science abstractions / mathematic or like mathematical abstractions. So once you start doing that kind of stuff, I think that the rest of the world just starts to look very simple, in the sense that, like, when you have words that actually you can read, like private, static, final, oh my gosh, it's just heavenly. Whereas I don't know if any of you have seen, actually, we're going to look at an example. We'll probably look at a couple examples in this episode of some, well, this is pretty basic, but maybe it's probably the precision and recall for time series. Let's see if we can find this. Precision and there it is. Okay, this paper is a NeurIPS paper that we published a while back. And it's actually really interesting because it's, in some sense, very simple. This is not, at least in my mind, almost all the papers that I have worked on, I've approached them just because I've thought about the problem and then thought, oh, we should have this thing. And then I do a search for it, and then I realize, that thing doesn't seem to exist. And then I start asking people, hey, does this thing exist? And then, and like really smart people, like Stan Zdonek, who, if you don't know who he is, Googling him, he's super. Actually, let's do that. We're going to go down so many rabbit holes. This is going to get wacky and awesome. Okay, so let's look up Stan Zdonek. Yeah, look at this. That's Nesame Totbull right there, who is the lead author of this paper. Look at that. So that's Nesame. She's one of Stan's former students. I believe, from Brown University. And so here's Stan Zdonek, and he is awesome. I really absolutely love this guy. I unfortunately, we kind of pivoted on some of the research area that we were working on, and so I didn't get to publish as many papers or do. Really, I don't really care that much about publishing papers as much as I care about like working with really awesome people. And so it was actually Nesame that introduced me to Stan, and he and I hit it off immediately, and then we just started doing some wacky stuff. And it's really interesting because his background is more in database systems, which is not exactly my background. Like, I mean, my PhD, my dissertation and stuff, and my like master's thesis, those types of things were in transactional memory, which is from, Morris Herlihy, which here's another, we've talked about Morris. And he did this thing. And transactional memory, like, it's sort of, it has foundations in databases. So in databases, look at all the awards this guy has won. Like, Morris, like, what about all the other people? Like, I think he's reached the limit on the Dijkstra Award. Like, 3 times. Like, at some point, do they have to cut him off and be like, okay, Morris, you can't win this again? Like, it's like, maybe it's a hat trick. So he's got the hat trick now, which is 3, right? So I think I actually joked with him about this when he won the last one. I think I sent him a text message and said, if you win it again, Morris, they're going to have to rename it to the Herlihy Prize, which I honestly think that there's probably going to be a Herlihy Prize. Anyway, so what's the point in all this? I'm not exactly sure, but here's where I was going. I was working with Morris at Brown, between Boulder and Brown. Almost actually, well, I'll save that for another conversation. So then I got connected to Stan. He's also at Brown, I think. Yeah, he's Brown. And Nesame did her PhD at Brown. And so we have a lot of love for Brown. I have advised a few different students there. In fact, working jointly with Stan and Nesame, TJ I think he was like a master's student. And now, I don't know. He was at Microsoft. Thus, some of my earlier comments about how I have friends at Microsoft. And I think that there's lots of awesome people at Microsoft. Doesn't necessarily mean that I agree with everything that they're doing, but good people. Okay, so going back to all of this, I started collaborating with Stan, and this whole series of work is probably, in my mind, one of the most curious and strange rabbit holes, explorations that I maybe have had in research, in that the work that we were doing, we had no intention at all of ever writing this paper. And it's actually because of the BMW issue that we were looking at last time that I got to sort of the conclusion of oh, I should talk about this story because it's, at least in my mind, it's somewhat amusing. Okay, so I'm going to keep the thing here so I can see if anybody wants to chat. Let me make sure that they know that it's not scary. Because sometimes I think at first, when there's like a small number of people, there's this overwhelming fear of saying something because you're going to suddenly be kind of like called out by the teacher. Whereas if there's a large number of people, there often is significantly less fear because you often have the view that there's too many people to hone in on anyone in particular. So they might have this fear of like, oh, there's not enough people talking. I don't want to chat because he's going to zoom in on me. So let's say, hi, folks. If you want to chat, I'd love to hear it. Don't feel any pressure or nervousness to drop a comment, drop a live comment. I promise I don't bite. Perfect. All right. So back to our discussion. So what happened is we were looking at Mercedes-Benz and we got to this for loop. And I was saying that we discussed this last time, interesting properties. I was actually discussing this with Taylor today. And that was actually, let's just see. I think Taylor was awake. Let me see. Let's just ping him in real time and see here. Hey T, I'm doing my first live stream on YouTube. If you're awake and available, hop on YouTube GTT and drop a comment. Question mark. We love the whole questions. Okay. Cool. Okay, so back to our train of thought over here on this conditional. So we saw this, and I was kind of explaining that Mentor tends to not find control expressions in loops. Oh, sweet. He just responded back. I think he's hopping on. He's like super pumped. Okay, cool. So hopefully T will be joining our live stream, and then he can start chatting up a storm. This will be fun. Okay. Oh, there he is. Hey, buddy. Awesome. First live stream. Feels like Nautica all over again. Don't you wish you typed in Dvorak too? Kidding. Okay. So, and T, we're talking about the Mercedes loop control expression, and we're about to dive into some of my code, which will take us on a fun and strange ride just to get you caught up. Okay. Oh, and please don't feel too much pressure to stick around for a long time, as I know you are also doing some critical work stuff for the BOD. Where we're going. Roads. Okay, cool. Great to have T there. I wonder if I can make him a moderator. Hold on, let's just see if I can like click something and make him a moderator. Add as moderator. Managing moderator. Can manage blocked words, chats. Also, yes, he's the boss. Okay, there you go. T, you are a boss level moderator now, FYI. And of course, he's watching this, but I'm like 30 seconds into the future. So he's probably seeing the chat about it first. And then, yeah. Okay, cool. So back to this. So we got this control expression in this loop. And I was going to try to make the point that, I try to have code that has significantly less complexity for loops. And then I thought, okay, in order to demonstrate this, I should probably look at code that I've written. And then what I did is I searched for the Paranom system that I built that does data synthesis, specifically for machine learning. The background on this, which we'll get to in a second, is it was used for a bunch of the work that I was just showing. So anyway, I started Googling Paranom for GitHub, and then I couldn't find it. And this was confusing to me. But then I found this site, Papers with Code. I'm going to maybe... Okay, cool. I'm going to just find a way to leave that active so I can see the chat potentially moving forward here. Okay, cool. I need this to kind of keep me on track so I just don't get lost. Getting promotion. Yep. That's how we roll, brother. Merely promotion speed. Okay. So I was Googling Paranom, and I was trying to find the source for it. And instead I found this thing. And I was like, okay, cool. So yeah, here's the Paranom paper, right? And then I was like, yeah, this is the paper. I looked at it, and I was thinking, okay, so where's the source for this? And then I was also noticing that this is Papers with Code, and it's saying no code implementation. And I was thinking, well, that's confusing because I thought I coded this and open sourced this. And I did. But I forgot that we renamed it to DATSA. Okay. So now, before we go down the rabbit hole of all of this fun stuff, I need to give a little bit of background on why Paranom came to be. And it's actually, in my mind, at least marginally amusing. Once I joined Intel back in like 2010 or so, 2010, as a research scientist for Intel Labs, they had mentioned when I was joining that they really like for their scientists to do patents. And at that point, I hadn't done any patents. I had maybe like a dozen peer-reviewed publications. Most of those were just like workshop papers. I had maybe like 2 conference papers and maybe 2 or 3, and only one that was like a regular paper at a sort of premier venue. What I'm trying to say is newbie, like put in a lot of work and was learning how to do research, but still pretty early in my career and kind of didn't really know what I was doing. Still don't really know what I'm doing, but far more courageous now to just dive into all this crazy stuff like this kind of thing. I think it would be actually really amusing to watch the beginning of this stream as I'm fumbling around. So I joined Intel, and I'm fascinated by this whole patent thing. I think mostly because I'd never done it before. And in my mind, I kind of thought that patents were sort of like this really big deal. And I remember some of my professors in both Brown, at Boulder, and other places were telling me that patents they essentially count as an equivalent for like a conference paper, in that they're really hard to get patents. They could take many years, and you essentially have to show almost all the things that you need to show for a research paper. And what that means is essentially with research papers, at least the research stuff that I tend to target, you have to have sort of some degree of novelty in the system that you're building. And then there's other things like rigor for scientific experimentation, compelling story, blah, blah, blah. But the key thing is that you have to have a novel scientific contribution. Otherwise, it's not research. You can have cool engineering implementations, which is engineering, but the research part is it's supposed to be sort of pushing knowledge forward. You're expanding the domain of knowledge. Now, this is not always the case, because you can have research papers that are like survey papers. You can also have research papers that are like a compositional novelty of existing engineering systems, that then their composition of these things creates a form of novelty scientifically, although the individual components themselves, none of them are necessarily novel. An example of that is our AutoPerf NeurIPS paper. I think that's right. Yeah, like I don't think we invented anything new. We just combined a whole bunch of advanced things. Like we combined autoencoders, performance analysis, and hardware performance counters all into this machine programming system. And maybe that had never been done before or something. So I guess what I'm trying to say is there should be some form of novelty in your research stuff. And then if it doesn't have any novelty, like if it's just an sort of like an engineering effort, it's probably not going to get accepted, at least not to like a tier 1 research venue. Okay. So how does this relate to patents? Well, patents, as I had understood it, follow the same kind of mechanism as research papers, is you have to have novelty, and there's actually a rigorous process for reviewing patents before they get approved by the patent office, at least in the United States. And I think that it's similar for many other countries. And the review process is similar to the review process of research papers in that you'll have a patent assessor or a team of assessors that will review your patent application and then try to ensure, that it has sort of scientific, technical, domain-specific novelty that would warrant a patent. And this is super important for patents, very much like research papers, but even more so with patents in that they need to make sure that the idea is not a duplication of an existing patent, because you don't want two patents or more than one patent that's essentially patenting the same idea, because then, like, one, the patent office should kind of never let that happen. And then two, think about like the legal dispute that could create is multiple parties be like, well, I have the patent. And then it could get real ugly real fast. And yes, of course, you could use the date of who was issued the patent first, but it's actually more complicated than that because you have ideas like first to discover versus first to submit. And I think now, I don't know, they changed it a little while back. And it used to be one and then they switched it to the other. I think it used to be the first to discover would supersede anyone else for like patent ownership. And so what this means is, and I'm really going down a rabbit hole here. What this would mean is imagine that Taylor comes up with an idea in 2024, and he has some sort of evidence in a real world way that he can leverage to demonstrate that he came up with the idea in 2024. Now, fast forward to 2025, in January, I submit a patent application on exactly the same idea. Then Taylor submits a patent application on his idea, which is the same as mine, but he does it, let's say, 3 months later after I submitted my patent application. The way that I think it used to work is it was first for discovery, meaning that what would probably happen is my patent would be issued first, and then Taylor's would be rejected, saying, oh, well, Goju already has this patent. And then Taylor would go back and say, well, I have evidence that I discovered this in 2024. And then they would look at my patent and say, oh, well, Goju, do you have that? And I'd be like, I don't have that. And then they'd yank my patent and then they would give it to Taylor. I think this is the way it used to be, first to discovery. Now I think it's first to submission. And so under the new rules, and again, I might be getting this backwards, but there was a change that happened, I want to say recently, but it could be like 5-6 years ago, where they inverted it. And so now I think it's the first to submit. So if you take the same scenario, Taylor has evidence of discovering the idea in 2024, but I submit the patent application in January 2025, and he doesn't submit it until, let's say, April. It doesn't matter that he discovered it a year earlier than I submitted it. All that matters is I submitted first. And for as like unfair as this might seem, I think that the first to discover is really tricky because, like, think about all the ways that you could try to articulate that you have discovered it. And then think about the ways that people might try to, like, become historical revisionists. I mean, I'm all about fostering goodwill, but patents can sometimes be a little bit of a big deal, especially if they're related to the success of various corporations for IP ownership, intellectual property ownership. So you can imagine how there could be some really intense legal issues that could emerge in fighting for who was the first to discover. Whereas under the principle of first to submit, it's super clear because it's just whoever submitted the patent application first. They get precedence. So I think that that's how it is now. And now we all understand a little bit more about patent law, or I've butchered the patent law parameters, and all the patent lawyers, which of course I am not a patent lawyer, can chime in the comments and tell me how wrong I am. Keep in mind though, I have done, I have some experience in patents, and I've worked with probably over 100 different patent lawyers in my career, because there was a time where I would get a lot of enjoyment from doing patents simply because, unlike research papers, and I'm just going to be totally honest here, patents in some ways would allow me to be lazy, because one of the things that I get sort of the most enjoyment from is thinking about really hard problems and then coming up with kind of like these crazy ideas on how to do something. And then in my head, I like to solve that problem in these really strange and unusual ways, but in ways that work. Like, not snake oil and not nonsense, but an idea that actually would work. And for a long time, maybe the first 10, 20 patents I worked on, what I would do is, how do I give, here, I wonder if, yeah, I'll just do that. Yeah. Oh, what does he say? Okay. From the interwebs, U.S. patent law is now first inventor to file. Yeah. First to file. That's right. First to file. So that I was getting the language wrong. First to file is what I meant from first to submit. So, and I think it used to be, first to discover, which is like, I think what T's describing here on the first to invent. And again, I think that the change actually kind of makes sense, because it's really hard to show in a demonstrable way that the evidence is not manufactured, or like somebody could have discovered it long before somebody else, but just not publicized it. You know, that's actually really common amongst inventors, because they're scared about the idea getting stolen, and then they'll work in isolation and kind of covet the idea. And sometimes they'll spend an inordinate amount of time trying to get it exactly right before they go ahead and submit. So yeah, there's a lot of caveats with it. So cool. Thanks T. Appreciate it. So while I'm at Intel, I start working on these patents, and I'm very much not a snake oil kind of guy. I don't do, like, every single patent that I've worked on, minimally, I would say, in my head, it fully makes sense. And oftentimes, you'll have to do at least a system diagram and clearly articulate how the thing will work, but you aren't necessarily required to build what's called an embodiment. So for any patent idea, oftentimes you have this general ideation part, which is sort of like, this is the core idea of the patent, and then you generally are required to give one example embodiment, which is sort of like, here's how you could build this thing concretely. But this is only potentially one example of many. So, for example, if you look at the original patent for a shovel, they describe what a shovel is and how it helps people dig stuff. And then they give one example embodiment of what a shovel is. Now, is that all embodiments? No, it's just one of many. And as we probably all know, there's a bazillion different ways to build a shovel. And what you generally try to argue with the patents, again, keep in mind, I have far too much experience and background in patents. I really don't do patents that much anymore. In fact, I don't know that I would say my feelings have changed about patents. It's complicated. I think that they can be useful in certain cases, but I think they can also be detrimental in others. It's complicated. So anyway, what you will often try to argue, or the patent lawyers will try to argue in the patent applications, is for generality. You want to get the largest scope that you can for a patent application, so then you have more coverage of essentially legal protection. You don't want it to be narrow. You want it to be as wide as possible. So then if other people kind of infringe, you can say, well, in this thing, it clearly covers this entire space and you're here, so stop doing that. Okay. Now, let's move on to DATSA or Paranom. So at this point, I want to say I had probably done, let's say maybe like 30 or 40 patents. And so this is becoming, I don't want to say like old hat for me, but I'm getting pretty comfortable with the patent process. I think at one point I was like the chair of the software engineering group or something. And I had run like many different think tanks for patent ideation, patent harvesting, things like that at Intel. So like I was pretty comfortable with this. So, and at this point, maybe I would say like 90% of the patent applications that I would submit would be approved. And part of that, again, is when I first started doing the patents, very much like first started doing the papers, the majority of the initial attempts are failures because I don't know what I'm doing. But just like with Taylor, I generally try to be quick study. And so I'll try something new and then I'll fail. And I'll work some more and I'll fail. And I'll fail. And slowly, each time I'm failing, I'm actually learning more and I'm failing like in different ways. So from the outside, it may look like, oh, you just keep failing. Boy, you're awful. But really, it's like, okay, this first one, failure at 40%. This next one, failure at 60%. Next one, 65%. Next one, 80%. And so what's actually happening is I'm getting closer and closer to the top. And so for the first dozen or so patent applications, it was just the same as my research papers, just constant rejection, which can be a bit disheartening. But at this point, I kind of have background in this, sort of know the process, and I think know how to maybe tell the story, or so I thought. Now, for patents at Intel, at least when I was there, it was a multi-phase process, and initially you'd have to be approved by like a principal engineer or a technical lead or something that's in your group. Maybe that's your manager or it's some higher up person. So me being like just a lowly research scientist, I think I had to go through this process where they would look at it and say, wow, this idea is terrible. Just don't even submit it. And then after you get the approval sort of locally from your team or whatever, if they approve it, then it goes to an actual patent review committee that are subject matter experts, SMEs, in the domain. And at Intel, there were, let's say, like 40 different domain groups of experts in these different areas. So like AI was one, hardware architecture. Actually, there are probably several for hardware architecture. One might be like storage, another might be power, like all of this stuff, right? There are many for software because there's like more low power software. Then there's like web software. There's high performance computing software. Like HPC is actually very sensitive because of constraints that the United States has on export control, limiting, having tighter embargo regulations on HPC things because of their potential to be supercomputers than they have with like commodity hardware. Anyway, these are all extraneous details, but hopefully we're all learning a ton about random patent things. So then after you get the local approval, you submit to the patent committee for whatever area you're in. And then you'd usually have a team of maybe 5 to 20 experts. Most of these folks are, they're like principal engineers, which is like a pretty big deal at Intel. It's like you have to be voted in by a committee. It's like a very serious thing. So if you ever see someone, it's often this way like Microsoft, Google, Amazon, a lot of the top tech companies have the same point. A lot of them for technical track is that to get to be principal and fellows, you have to be voted in. So your manager can't do this by themselves. They have to put together a packet. It's almost like you're trying to get tenure as a professor. It's a pretty rigorous thing. So anyway, the patent committee's usually made up of principal engineers or above. These are very seasoned people that would look at this. And so this particular paper was a patent application. And when I originally wrote the patent application, I basically was coming up with this idea. And the idea I had was that we need better data synthesizers for machine learning, specifically for time series work. So as many of you know, and if Mur's watching or will be watching the recorded version of this, I've had a deep love for things that are time series for a very long time. So this paper, I think I submitted to arXiv, in January 2018, which means I was probably working on this as early as 2016. And if you have a background in machine learning, then you'll know long short-term memories are principally for their like sequence-to-sequence models. Basically, they're often used for temporal analysis. And I think I'll probably talk about this somewhere. In fact, a lot of people argue that prior to modern-day transformers, which are the foundation of language models, the state-of-the-art model in neural network architecture before transformers were discovered were long short-term memories. And in fact, that's why we were using long short-term memories here, because transformers hadn't been invented yet. Or minimally, we weren't aware of them existing. And then after they did show up on the scene, a lot of people shifted from doing work in long short-term memories to then transformers. Okay. This is a long preamble to get to this story, but hopefully I've made this at least not super boring. Okay, so I write this paper essentially as a patent, and I submit it, and I get this really interesting feedback from the patent committee. The patent committee tells me, we love this idea. This is super cool, but it can't be built. This idea that you're proposing, it's not buildable. And so I said, really now? So it can't be built. Challenge accepted. So I then, mostly because I just wanted to get the patent approved, I wasn't trying to flex or create unnecessary conflict or be like, I'll show you. But I really thought that this would be a good patent for Intel to have, because I thought that temporal models for machine learning were the future, and having synthetic data generators like one of the most important things. And the truth is, since we created Paranom or DATSA while I was at Intel, we had used it dozens of times for massive data generation. I mean, on the order of billions, if not trillions, of data points. In fact, some of our early program synthesis work was based on data that DATSA was generating as synthetic instructions for a synthetic program or an artificial program that didn't exist. More on that later. So I get the feedback from the patent committee, and they basically are saying, yeah, we love the idea, but yeah, you can't, this is not possible to build it the way you're describing it. So I say, challenge accepted. And I then do a weekend hackathon and build this guy. And basically what I build is like pretty much exactly what I described here. Is like, I literally recall that when I was building this, I was looking at my system design to remind me, how does this work again? What am I building? And so I literally just was looking at this thing here and saying, okay, cool. So I've got like this part built. Now, what do I do? And so it's literally, I'm just following the flow chart, right? I'm just like, so I've got to now build the normal data over here, and this is how it's going to work. And then I'm going to do the anomalous stuff over here. And then it's going to have like slightly different types of behaviors. And then I'm going to do this merger of the normal and anomalous data. And then it's going to essentially converge the results in like the correct interleavings, because these are being generated separately, potentially on multiple different nodes. And yeah, thanks T. Yeah, I'm pretty pumped about this stuff too, but pretty nerdy, but super fun. So I build this thing, and what I do is, and I want to share that there's actually some really interesting, there's one part in this paper that I was looking at that reminds me of some stuff that it might have been like a preamble to some of the stuff that I've been thinking about with semi-trust. And it has a little bit to do with this data uniqueness part. So let's just take a quick look at this. So here I'm describing what the Paranom system is going to do. It's now called DATSA because people really didn't like Paranom. By the way, the reason we called it Paranom is it's a parallel anomaly dataset generator. So it's like the par part for the parallel and the anom part for anomaly. Paranom. I mean, yeah, okay, it's probably a terrible name, but DATSA, I think people hated that name just as much or disliked it, because then people were saying it reminds them of a car, like Datsun or something. So whatever. I guess the point is damned if you do, damned if you don't. People are not going to like your names. Just find the name that you like and go with that. Thus, Goju. Whether people like it or not doesn't matter. I like it, and it's an abbreviation of my last name and my first name, and it's mostly a non-collision inducing 4-letter name. Super great for email, writing on a whiteboard, like Prof G, Dr. G, or just Goju. Telling you, like, I know Justin is pretty short too, but those 2 letters plus collisions on Justin, and let's just say that there's one Justin out there. I'm not going to say which. I'm not like a super fan of that guy, and so having a slight amount of disassociation gives me the right kind of warm and fuzzies. We'll leave it at that. Okay, so here we're describing the importance of data sets in terms of machine learning just in general, and then also for anomaly detection. And in particular, we're talking about, one of the biggest issues that you have for anomaly detection systems. And keep in mind, this is a space that if you look at my patent list and publication list, I probably have at least 10 publications in the space of anomaly detection, and I probably have 30 or 40 patents in anomaly detection. And I've taught anomaly detection theory as well as practice at I do it a little bit at the university that I'm at now, but before that, I taught it at Penn, a little bit at MIT, Berkeley, and a couple other places. So this is an area that I have some background in. And one of the challenges that you have with anomaly detection, especially real world anomaly detection, not these pretend sandboxed sort of no disrespect to my academic friends, and I'm an academic, but more like academic, very simple problems. For problems that are not like that, the ones that are in the real world, what you often run into with anomaly detection is that, and this is me working with dozens of different people, you often do not have data that is anomalous. Or if you do, you often don't even know which data is anomalous. So I worked with many different folks across many different domains that would have enormous amounts of data. We're talking like petabytes, maybe even exabytes. I was working with the BMW autonomous vehicle division in Silicon Valley, and I think that they had more than petabytes of data. But they, at the time, or at least the problems I was working on, they didn't necessarily know which of their data is anomalous, if any of it was, and they didn't have anomalous data flagged in the data that they had, just at all. So, in my mind, I thought one thing that would be really helpful is if you could have a synthetic data generator that could generate the anomalous data for you. And the idea at a high level that I had, and we'll get to how this actually happened, and we started to build this in a moment, but the idea would be that in the early stages, you would have some kind of understanding of the signature of the data that you're working on. And so you'd be able to sort of envision what anomalous data would look like. And then you could programmatically build it. So then the synthetic data generator would build the type of anomalous data. Sorry, this is the anomalous side. This is the normal side. It would generate the type of anomalous data that you thought would be necessary or helpful to learn on. And the reason for this is, while there are techniques in machine learning to learn without anomalous data, in fact, the zero positive learning paper, zero positive learning paper, this one? Yeah, this one actually learns completely without anomalous data. That's what zero positive means. Another name for this that's used in the literature is this thing called one-class classification. And the idea of one-class classification is you have a machine learning system that learns entirely on one class of problems. And in many cases, it can be the good class. So imagine building a spam filter for email, and all you have are good emails. So you learn just the good class. That would be one class. And then anything that falls out of the one class, you learn implicitly as non-good class. Similar idea with zero positive learning. It's slightly different in that zero positive is specific for anomaly detection, whereas one class classification is a technique that you can use in general machine learning. It doesn't have to be related to AD, anomaly detection. And this is important because you can have bifurcated spaces, binary spaces that are not anomalous, and use one class classification very effectively. Zero positive learning has properties that make it more specific for anomaly detection. So if you have equal distribution or not anomalous distribution of data for some space, zero positive learning is not likely going to be as effective as one class classification because it has a bias toward learning anomalous spaces rather than spaces that are not anomalous, if that makes sense. Okay, and if not, you can Google about all this stuff afterwards. All right, so we have this system, and I build this, and then I resubmit it to the patent group after I did like a weekend hackathon. And in fact, one of the early versions of the patent was like this paper. I think I even used this example, is I said, okay, and I took this data, this is like NASA data that I found online of their space shuttle, and I was trying to figure out if I could identify some anomalous event with one of their sensors. And what I think I did is, I'm just trying to figure out what the differences are here. Yeah. So this, yeah, right. This is the original data. And these points here are, I think, like things that are anomalous. And so we train on this, and then we test on this, and we miss these 6 anomalies. And so here is essentially a long short-term memory system that, oh yeah, it looks like maybe it flags these 2 here, but then it misses these other 4 ish. Then what I did is I took Paranom, and I then determined essentially what a signature of anomalous data might look like. And I programmatically inserted those into the original training data. The idea is that if you have a sense of what the anomalous data might look like, then you can potentially inject it into this training data, even though it's fully synthetic, right? But then the system will learn on this. And then if you test it against the same testing data, so this testing data has not changed, but we've augmented the training data to use some of the injected anomalies that I synthesized with Paranom at precisely the right sort of interval based on things that I had observed by looking at the data, then the new long short-term memory model that's built could identify essentially all 6 of these anomalies. Or maybe what it looks like is that this one identified maybe, it looks like it could get close to all 6. Maybe it struggled a little bit more with this first one. These are the analog signals for the anomaly probabilities. These are the digital signals. So a digital signal is like, it just essentially is using something like a softmax to do rounded probabilities, which then tell you either it is an anomaly or it's not. Whereas these other ones are like, I don't know, it's 30%. Yeah, it's like 40% anomaly. That actually could be enough of a signal for it to flag as an anomaly. But here we're basically trying to show if you had a flat softmax function that switches the binary output of anomalous or non-anomalous exactly at the 50% range, what would you get? And so in the original, you would still find the first 2 anomalies, but you'd miss all the other 4. In this one, you miss the first anomaly, but you detect the second one and then the other 4. And so then the results are essentially that in the original, keep in mind accuracy for anomaly detection is not necessarily all that useful, because you can have a system that has nearly 99% accuracy for an anomaly detection system and just say that every event is non-anomalous. It's super easy to do. And it's why accuracy is not a great metric for anomaly detection systems, but it's continued to be used in the literature today. This is also part of the reason why we wrote this paper on rewriting the rules for precision and recall for time series. But we're not yet at that point in the story. So let's go back to this. So the accuracy improvement is like only like 4%, less than 4%. But it has an order of magnitude improvement in recall. That is a lot. So it goes from 0.02 to 0.4. That is a massive increase when you think about just the order of magnitude jump. And then before, what we had is we had perfect precision, and precision is the idea, if I recall correctly, recall and precision. And keep in mind, I supposedly know a thing or two about this because I was the guy behind this thing, but truthfully, I can't actually. Oh, let's cheat and let's look at the. I was just going to wing it and not know, but this paper will tell us. Okay, here we go. Informally, precision is the fraction of all detected anomalies that are real anomalies, whereas recall is the fraction of all real anomalies that are successfully detected. Okay, so we're talking about recall. We had a good score. Precision went down a little bit. Precision is a fraction of all detected anomalies that are real anomalies. Yes, so that's actually what I was going to kind of guess, truthfully. And the reason why it went down is that in the original, what you can see is that it only guesses on these 2. And so it doesn't guess wrong anywhere else. That's essentially precision. So this has a 100% precision score because every time it guesses that there is an anomaly, it was right. Whereas this other system, you can see it has a couple misses. It's like, oh, I think there's one here. And it's like, nah, there isn't one. It's here. And then there's this other one. It's like, oh, I think it's here, or maybe that I don't know. But you can see that it like it guesses wrong at least once, where this system doesn't guess wrong at all. However, it also catches these other 4, and this one doesn't catch it at all. And this is why you use the F1 score generally. Is the F1 score is essentially the just average of these two numbers. That basically, what it does is it keeps people from gaming the system. That the way to game the recall is, so the recall is, you have to make sure that every time let's look at the definition again. This is awesome. Supposedly I know this stuff pretty well. Clearly not. Okay, so recall is the fraction of all real anomalies that are successfully detected. Right. Yeah, so the way to game recall is you flag everything as anomalous. You get a perfect score for recall. You'll be wrong a lot, but you'll game recall. That'll drop your precision score way down, but recall you'll get perfect score. Okay. With precision, the way to game precision is like exactly the opposite. Is you basically, what is it? You only guess that it's an anomaly if you are absolutely certain that it is. And for the most part, you just say everything is not an anomaly. And then you can game the precision. And you'll get 100% on this. Now, the trick is that you can't game these together. In order to build a system that actually maximizes both of these, it has to sort of be a real system because they're opposites of each other. That if you're gaming for recall, you can't game for precision. If you game for precision, you can't game for recall. This is why we use the F1 score or the F beta score. F beta score is basically we control the ratio of which one's more important, recall or precision. But just generally think like F1. Yeah, and by the way, F beta is the shorthand notation for this. Beta essentially implies what the ratio is of the recall and precision. That's why it'll be 0.1, but that's not a constant value. It could be like 0.3, 0.005. It's whatever you want the beta to be. Again, it's the ratio. But I think it can be common to use have beta equal 0.1 for the F beta score. But a lot of people just use F1. And so the other big thing is that this has an order of magnitude improved efficiency for the F1 score. And that is it's like, I mean, this is close to a 20x improvement in efficiency for the F1 score. This is like a notable kind of improvement, at least in my mind. So this then, when I submitted this, because they were like, you can't build it. And I was like, okay, I'll build it then. So I built it. And in case you guys don't believe that I built it, here it is. And look, if you actually go into the examples, check this out. Is it easy? Space shuttle. Here's the space shuttle example. This is the actual space shuttle data that I apologize for this. This is terrible code. This is really, this is not good code. But what I did, because I'm lazy, let me just explain myself before you crucify me. It was all in just a raw data file. And DATSA uses code for the normal and anomalous data. And so I had to generate essentially what the time series values would be. So I just wrote a quick parser that basically parsed out that data file and then wrote this switch. and just did all this. So this is, I basically wrote a code synthesizer to then, and this was actually part of the thing that I was going to do next. Is the first piece was to build DATSA so that it would start to synthesize the data. Then the next step is I would build some other system that would learn what the data should be, and then it would synthesize the code that would be used for DATSA. And so basically the whole thing is just automated. Like, again, I'm not wired the correct way in my head. I can go, I mean, I'm sure T can attest for that. So once you get caught up, please let them all know that, yes, I'm not. I mean, like, look, it's 1 a.m. on a Saturday night, Sunday morning, and we're going down the depths of, this space shuttle example so you can see how real this is. So that's basically what this is that this is the data that I took, I think, from NASA to then, and this is real. Like, this isn't pretend. This is like a real, meandering down the rabbit hole. Yes, 100%. That's what we're doing. Okay, so I showed this. This is real data. I built it. You can see all the code over there. Then I resubmitted the patent application, and they approved it, which was cool, right? Okay. Now, it goes actually even further than this. And once we get a little bit further, I promise I'm going to stop, because I actually have something really critical that I need to submit to the board that Taylor knows all about. And I think I have to submit it by like midday tomorrow. But doing GTT stuff is higher priority than early board stuff, which I have to say really like low volume, because I know actually the Merly board even is watching the GTT episode. So, hey, Merly board, don't worry, we're going to get it done. Yeah. Okay, so we build this thing, and we do the patent. And then what we do is we have this this SysML conference that's being formed at the place I hang out at these days, and we're encouraged to submit this. And so we submit this, and lo and behold, I get my second rejection. That's right. So first rejection on Paranom I get because the patent committee is like, nope, not real. Then I build the system. I'm like, okay, it's real. It has value. I submit it to like these guys, clearly these, like, I don't know how I teach at this place. They clearly don't like me that much, right? So they reject this, and I'm thinking, I'm really striking out here with this Paranom thing. Well, the more complete version of this story is that we did go a little crazy on submitting things to this, because they were just like short papers this year, and we were like, we could write a whole bunch of short papers. Plus, it's local to us, and we generally like I have enjoyed hanging out over there quite a bit. So what we did is we submitted 4 papers this year, the year that we did this. And what happened is, oh, and by the way, this is the thing. This is the conference. And I want to say, I should probably come back to this. But this is the first time that I saw Professor Daly give a talk in real life. And yeah, we'll leave it at that. I did quite enjoy Professor Jordan's talk absolutely loved this. I loved this. This is maybe one of the first times I heard someone as prominent as he's like a full professor at Berkeley, wildly influential person in the space of machine learning, and ardent advocate against the use of the word AI. He really, at least this is how he thought in 2018. I think he spent half of his talk talking about how we should not use the term AI. It's completely disingenuous. We haven't built an artificial intelligence anything, and it's really machine learning. And the truth is, I quite agree with him. We have built a machine learning. This is also part of the reason why I call it machine programming. I mean, in today's world, it's sort of this ubiquitous sort of AI thing, and I'm kind of forced, or maybe not forced, but there's only so much time you should spend fighting the waves, right? Fighting the tide. At some point, you just kind of like, okay, look, I know that it's not great, but whatever. Anyway, so I actually sat through all of these talks, and they were super awesome. This is actually where I first met Dawn Song, who I absolutely, I'm a huge fan of Professor Song. She and I grabbed her after her talk. It was so good, and was like, we need to collaborate. And then we did. We started collaborating. I started working with some of her students. And in fact, there's one of her postdocs, Mindu, that we just submitted some workshop for, I think it's KDD, knowledge something something. I should probably know because the workshop was accepted, but I don't know. I don't think maybe I've had a paper there. I don't know. You know, when you get to my age, it's all just a blur. But I did give an invited talk for my research group at Berkeley for Dawn Song's group, and then we started collaborating with her team. She's done a huge amount of work in anomaly detection as well. She does a lot of security stuff these days. I think she has a security startup. Is very, really incredible individual. I think she's also a MacArthur genius. Like she's won the MacArthur Genius Award, which if you don't know about it, you can Google it, and it's pretty cool because it's like a peer elected thing, and it's super hush hush that you can't nominate yourself, and oftentimes the nominees don't even know that they're being nominated, and people only find out. They have like some pretty strict rules. They only find out like after they've won it. It's it's an interesting award. I don't know that I like the genius part about it, but nobody asked me like what I thought when they were coming off the name. And then there were some other talks. Jeff Dean spoke at the end. He gave, I think, a pretty nice talk. And he is a pretty prominent figure at Google. Although I think he's had some better PR days after some of the stuff that Google and Google Brain were running into with ethics on responsible AI. But I'll say no more about that. If you're curious, you can explore that rabbit hole on your own. And then the closing remarks, I want to just mention this is like, I'm a huge fan of Matai Zaharia. And I want to say that it has nothing to do with the fact that supposedly he's a billionaire. I really don't care about that at all. He's one of as far as him being a billionaire, he and Jan Stoica co-founded Databricks many years ago, as well as with Ollie Gost, I think, who's the current CEO. I think he was a co-founder in it. Anyway, I'm a huge fan of Matai because Matai and I started working closely together when he was creating SysML, because SysML is, I mean, it's the brainchild of many people, but Matai was doing a lot of driving on it. And then I was creating some of the machine programming stuff. And so he and I were talking about, we were both had never really done this type of thing at this scale. And so he was teaching me stuff and I was sharing. So like, again, I don't really care about money. It's sort of like a necessary evil, but the people in my inner circle, the people that I really like Don Song and Matai Zaharia and some other folks, Taylor Dolezal, it's not based on their wealth. It's just based on how cool they are as far as just being really awesome people with great ideas, being kind of like visionaries. So anyway, going back to my paper getting rejected. By the way, I think Matai Zaharia was like the chair of the program committee this year. So if anybody's curious about like nepotism in these conferences, if this is my guy, why did my paper get rejected? Well, it turns out, like I was saying, we had submitted 4 papers, and so one paper got in, the second paper got in, a third paper got in. And so what they told me is, you already had the most accepted number of papers. And if we would have given you 4, especially when the 4th is a solo authorship, it would have been like completely unfair. And so we felt like it would be much better if we accept the other ones that have like your grad students and other people like junior scientists that you're working with. Like Lindsay was early career research scientist, Guy Katz is a postdoc at Stanford. And so like, and then the other papers, like my student at Brown. So they're like, we figured you could accept the loss by us rejecting the one that was the solo author. Makes sense. I still think it could have got in, but okay. Like, so yeah, instead of like, there's one version of history, which is not telling the whole story, which is damn that SysML group for rejecting this. And then there's this other story that it's like, okay, Goju, like, you need to chill out, buddy. You're batting 750 and you want to be batting 1,000. Like, just take a breath and give other people a chance. So, and I think we did look at it, and I think, yeah, I think I tied somebody this year with the most. No, yeah, exactly. The most number of accepted papers this year, and it might have been like Michael Jordan. So, and on top of that, I have since gone on to, I think I've been on the SysML. I think they renamed it to MLSys. I think I've been on the MLSys program committee for like every year since this year. So since from 2019 until, yeah, now, except for 1 year. I think it was the year that I left Intel and was creating Merly. And I think part of it is, this is before I started working, teaching at this place. They couldn't find me. And so nobody knew what like my email address was. So it went to dev null because my Intel email was no longer active. Anyway, yeah. Interesting stories. Okay. Now, a couple more pieces, and then we're going to wrap this up. This gives you a little bit of the story of DATSA and Paranom, and then the SysML ML sys stuff, which is cool. But I wanted to share like one final piece, and that is that one of the papers that we submitted and was accepted. Oh, this is cool. I didn't even know that Kraska was there that year. Huh. Yeah, this is my very good friend, Tim Kraska. I just absolutely love this guy. He's just way smarter than me, way more knowledgeable than I am, way more graceful, just all around, just sort of a better. Uh, oh, look, and I know Sarah Bagsorky too. She's a fellow colleague at Intel Labs. Yeah, I don't know that I can. Okay, Goju, stop. Okay, so for this conference, one of the papers we got accepted was this one. And this paper is one of the anomaly detection systems that we were building and was being prototyped by a very large automobile manufacturer that was doing research systems for autonomous vehicles. And I'll leave it at that. Yeah. But pretty big automobile manufacturer, and I think that this system was used for their research autonomous vehicle exploration. And they pulled us in from Intel because of our background in anomaly detection, because they were really good with autonomous vehicles, but they didn't necessarily have the same background that we had for AD. And then so we collaborated with them for some time, which is awesome. Okay, now, what I think is quite interesting about this is when we wrote this paper, as I think I was mentioning before, what often matters when you're doing advanced scientific stuff is not that you understand all of these silly math things that look potentially super hard, or you understand all of these various pictures and can properly label all that stuff. Like if we go to this other paper here, like that you can fully describe this equation and like this, whatever this stuff is, and all these fancy symbols, and like, look, things are getting wacky. What is all this nonsense, right? Like this stuff, these fine details, they matter. But what matters more, at least in my opinion, is that you have a strong intuition about what you're supposed to be kind of doing. Okay, cool. Hi, Tyler. Thanks for joining, buddy. So, as I was explaining before, you can get to all these details later, but the key thing, I think, is to have the intuition first, because just understanding this stuff and like mastering these equations or whatever, that's cool-ish. But if you don't grok the intuition, then it doesn't matter if you've memorized these equations, because the equations like won't make sense. You won't have like the ability to sort of practically apply them. All right. The reason why I'm sharing this is when we were writing this other paper, we were getting these results. Yeah, down here, where we had greenhouse compared to this vanilla long short-term memory anomaly detector for these like Twitter. This was like, what was this? These were. What was this? I can't remember. It was some sort of anomalous event where I think something happened with. Maybe this is Apple stock and Twitter at the same time. Yeah, so something was going on there. And then the second one was there's some sort of anomalous event that happened with the New York City taxis. And as we were building the system, with me having, I think, a pretty strong intuition on the system we were building and how it was going to be better than long short-term memory, vanilla long short-term memories, we started getting these results. And as you can see, like we look at the F1 score, is the Greenhouse actually performs, what is it, worse for the F1 score than long short-term anomaly detection. And then Greenhouse performs worse in the F1 score than long short-term anomaly detection. And I think that, I mean, wasn't this, our thing was the Greenhouse. And maybe the part of the reason why this paper got accepted is sometimes showing results that's like your system, you explored something and it didn't work can be somewhat helpful. Yes, this, or maybe what we did is we combined something to get this LSTM AD. Whatever the case is, the takeaway. Yeah. Okay. Oh, okay. I recall now. So let me back up. The difference was Greenhouse was a zero positive learning system, which we talked about before, is an anomaly detection system that does not have any anomalous data points in it. So it learns completely in a one class classifier kind of sense. I'm sorry if I committed a mistake. English is not my. Do you work on this? Oh, yeah. So let's say, quick thing to Tyler. Yep. This is one of the papers, one of my former students. Oh, I guess. Okay. Let me back up and explain. On Nautica, when I used to do this, I never, they couldn't see me or hear me. And so I'd have to type back. And now I've realized in real time, oh, I can just speak and respond. I don't necessarily need to speak and respond and type it. So yeah, Tyler, I'm one of the authors on this, but principally it's, this is me just laughing out loud at myself. I am an idiot. Yeah, and I'm leaning in. Yeah, this is one of my former students' works. TJ, who was a grad student at Brown, and then he joined Microsoft. I'm not sure where he is today. And I'm this guy here, and then these are some of my other colleagues. So that's kind of the story. And you did not commit a mistake at all. This is part of the purpose of all this stream live chat stuff. Okay, so with the LSTM AD, the difference is, now I remember why this was accepted for publication, is that this included anomalous data, and the Greenhouse system did not. It had no anomalous data. It just had the original data. So what we did is we augmented LSTM AD data to inject anomalous events, and we did that using Paranom, right? As I was mentioning, we started using this like crazy because I'm all about building systems that have real value. And then since the Intel Patent Committee was like, well, you know, it can't be built, then I kind of had to build it. So then we had it and we were like, well, let's just start using it. So we started using it. And that was how we got the LSTM AD system, is we had synthetically generated anomalies, and then we showed that zero positive learning in the Greenhouse system could be almost as effective as this LSTM AD thing, even though we were clearly handicapped in that we didn't have the anomalous data. Okay. Now, the part that I think was maybe the most interesting for me. Oh yeah, and it also used smaller data. Yeah, this I remember this now. Greenhouse used significantly smaller training data, 25% and 55% of LSTM AD for both of these cases. That's also like a notable improvement in terms of the model accuracy. But even with this, I still was annoyed because I thought that Greenhouse should have performed better than the long short-term anomaly detection system because of the design of the Greenhouse system. And I can't remember exactly how it works off the top of my head. We could stare at this. We can do this next time. So the intuition, going back to the intuition I had was Greenhouse should perform better. This doesn't make sense. And then I started to deeply stare at precision and recall and the F1 score, specifically as it relates to time series. And it was at that point that I sort of had that revelation of like, precision and recall fundamentally do not work for time series. They work extremely well for discrete systems, but they do not work well at all for continuous systems. This goes back to the fireside chat that Jan LeCun was having with Bill Daly, and how Jan was saying these systems, they don't work well with continuous spaces, and they tend to work very well with discrete things. And he was making the comparison, I think, to video. I don't really care that much about video. I mean, I guess I should with this YouTube thing, but I care about continuous systems related to time passing for code data, and for repository software evolution. So this kind of continuous system, this is a continuous system, as well as the actual code data, which, you know, if we go into any of these, this can also be seen as a continuous system if you think about the execution of instructions as they were to happen over time. These are essentially the two axes that I refer to on machine programming and what I teach at the university. So the observation I basically had, and keep in mind, our goal was simply to build Greenhouse, which we did. And we got it accepted as the short paper for this fancy conference that is, yeah, I mean, it's a pretty good conference now. I mean, at least minimally, it's important enough for me to remain on the program committee for like 6-7 years. But I was not happy with these results. It didn't match my intuition. Something was wrong. So at that point, I basically went back to the team and said, we're not done. This should be better. We need to rewrite the mathematical foundations of precision and recall so it works for time series. And the team, I think at the time, was like, "You're nuts, dude. Like, what? We've won. Okay, Goju, just like chill." And I was like, "No, it's not right. This should be better." And this is really holding people back, that these long short-term memories and these temporal systems are actually performing much better than people think, because they're using the wrong metrics of analysis, precision and recall, and this F1, and these work for discrete systems. And so, yeah, Tyler, I do a couple of different things. So I teach at one of these universities and do research there. And I also am like the head scientific guy at this company, this company here. Yeah. So I nerd out quite a bit. And actually my chief of staff and the head of product for this thing is on the chat here as well. That's Taylor. So yeah, you're in good company with all of us nerds. So after we got these results, and I was like, I am convinced that we're doing way better than what these results show. I think that this is not right. So I went back to the team, and we spent the next 2 years. So this says 2018. I maybe what we did is we sat on the greenhouse paper. Yeah, that might have been what we did. We might have sat on the green. I can't remember, but basically it was 2 years. We built the greenhouse system in like no time flat. And by the way, the other piece that I think I injected in there is the Paranom system, or the DATSA system, was essential to the greenhouse system because we used it for the data generation that we then trained the LSTM AD on. And so as you can start to see, like, this is kind of the way that I think about these things, is they're just like they're all kind of part of the same story. It's all fluid. Like the thing that Taylor and I are working on, which is we call it the GTM packet generator. This does this automatic packet construction in a PDF form for these repositories. And that's pretty cool, I think. But that's fundamentally based off of all of this stuff. And the higher order bit is that once you get the right infrastructure in place, if you design it the right way, then you can likely start to do these various kind of spiking out things. Like, for example, we have, I think, integration of Mentor in GitHub for GitHub Actions for CI/CD pipelines. And that's because the Mentor system, this is basically just a fancy UI on the core system, which provides a bunch of these ABIs, these application binary interfaces. So when we go back to this story, this paper was the result, in some sense, of, at least part of it was the result of things that we could synthesize from this paper. And then once we had this paper, we realized, and again, this is like, I think, how research and how a lot of the stuff that we do at Merle and the stuff that I do at the university ends up, is it's not like we start working on a problem and then we solve that problem and say, like, we're done. The way that I kind of think about it, and T can attest to this, is like, it literally just becomes a domino effect. As we build this thing and think, oh, well, now we can do this thing. And so, oh, let's build that thing. Or, well, what would be really cool is if we had this thing. And so each idea springboards onto another idea. And some of them come in strange orders. So, for example, this paper is defining the core mathematics of how we think precision and recall should work for time series. And by the way, this was published at NeurIPS, which is like some people argue is maybe the #1 machine learning conference, research conference. And, whether or not that's true, I mean, it's anybody's guess, but it was also accepted like as a spotlight paper, which is sort of this special class of, not only do we like this paper, we think it's sort of pretty good. And I think Nesame presented in front of the NeurIPS audience, and I want to say there were several thousand people in that room when she was presenting. Just to give you a sense, I think NeurIPS. I think I didn't accept the NeurIPS invitation to serve on their program committee this year. Just not that I have an issue with NeurIPS. NeurIPS is great, but just too busy But in the past, I think NeurIPS was getting on the order of, this is like tens of thousands of paper submissions, and the attendance, it's crazy. The number of people that were going, especially for a research conference like this type of attendance may not be unusual for like developer conferences for things maybe like KubeCon, which is huge. I think T can probably tell us what the attendance for that is. I think it's tens of thousands in Northern America and maybe something similar for Europe. So those numbers, I think I've seen those before. Yeah, 12.5K, that's a lot. And for research conferences, like for example with SysML, when I was not getting this paper accepted there, but this other one, I think there were a total of maybe a few hundred people, maybe something like that. Tyler, the greenhouse, I think we called it greenhouse because it used significantly less data. And so the training compute overhead was upwards of 50% less than the other long short-term memory. And as far as the greenhouse system, what it does is it detects anomalies in different types of data. So in this case, we had two different types of anomalies. Had this anomaly that I think was in some Twitter event. I think it was like Apple stock, or they announced the iPhone, something Apple related. I think that's what this is. Let's check this out. AAPL stock. Is that right? Where's the little index thing? How am I not seeing? Oh, there it is. Okay, yeah. Yeah, so I think it was something like Apple stock skyrocketed and Twitter like froze or broke because of it. And then this New York city taxi, there was some unusual event that happened that caused the taxis, I think, to experience some sort of massive slowdown. So that's sort of like the high level of it. I'll drop a link in the chat, Tyler, so you can check it out. But this is part of like this larger story of some of the stuff that we were working on. Anyway, the last piece is that then from there, we built this precision and recall for time series system. And this is probably, in some sense, the most prominent research that we've published from that series of papers. And yeah, look at this. You even have, look at this. We even, yeah, so like I was really a stickler. I was like, these results are not right. Like they need to be better. And so we went back and we looked at this and then we reran these things. And I think we showed that like greenhouse was better or something. Then, yeah, like I'm in my mind, clearly I like have the iron trap and I won't let things go. And so, yeah, that's basically the summary of our story for tonight anyway. And yeah, this paper, I think, has gone on to, I think it's being used, the algorithms. This is also open source, by the way. What do we call this? Okay, let's see. It's like precision. What is this? This is, oh, that's cool. What is this? This is the unofficial Python implementation. That's cool. Yeah. Hey, let's start this. That's pretty awesome. Okay, yeah, sure. What it's gonna? Okay, all right. Okay, we're not gonna log in. Um, yeah, that's pretty awesome. I had no idea that this existed. So yeah, like I was saying, is that there's some people I think that are using this, and that's cool that they ported it to Python. I think our original system was like in C, C++, something like that. Let's see here, GitHub. Where is ours? That's so great that the Python one shows up before ours. I guess maybe that's a sign of the times. That no, I don't think this is ours either. Maybe ours doesn't exist. Oh, hey, look. Yes, here we go. Okay, so yeah, maybe this is the issue is they like deprecated it or something. But yeah, it's being deprecated. I'm not sure why they did that, but I no longer work there, so they can do whatever they like. But so if you're interested in this precision recall for time series thing, you can check this out. We'll probably use this at Merly as we start to explore some of the time series, the temporal axes for machine programming. But of course, we'll use the Python implementation. Just kidding. We'll for sure use the. I think I actually was involved in writing some of this. I think, yeah. Yeah, that's right. Yep. We can rewrite it in Go or something. But yeah, I think Nesame wrote the original version, and then I came in and C++ized a little bit of it. Anyway, excellent. So this has been super fantastic. We've been going for just slightly over 2 hours. And I also recorded this as well as doing the stream. I don't even know if that's necessary because this is our first stream and I have no idea how this works. But I think we're going to find out very shortly because I'm going to end the stream now. I'm going to click a button somewhere. Yeah, this end stream button. And then we will see what happens. So Tyler, and the other 5 folks. That's cool. Look, we got like 600 views. Wow, this is not bad for our first stream. I'll figure out what this resolution thing is. But I may try to do another stream tomorrow night after I finish some of this other, board related stuff. But I actually quite like the stream. Yep. No, thank you, T, for joining. I quite like the interactivity of the stream environment, and since I think T and Tyler, you know now, I don't really edit. I don't like editing the videos. I like the more authentic presentation of all the errors in full disclosure kind of thing. Just feels more genuine. So I was basically doing a streamed form. It was just locally streamed. And so now we can do it where we can actually make it interactive. And plus, I think it's far more interesting with people talking to me and having random comments. So thanks, everybody. This was super great. And we might be doing this again. Oh, do you want to make a special appearance, buddy? Come on, buddy. Let's just see if we get this little doggy. Come here. I gave him a bath. We did like a quick 3-mile run. Merle, come here, buddy. Come here. Come on. Come here. Come here. Here he comes. He's making a slow way. Here he is, guys. Here he is. Here's the doggy. Yes. So he's cleaner now. He smells much better. He was a little bit angry because he thinks that he's a cat, and somehow is terrified of getting a bath in the kitchen sink. I don't know what the deal is with that, but now we have Merle the dog, we have Merle the company, and we have this Merle guy that is gonna now go to bed. So thanks everybody for joining. GTTers, we're off to the races. Oh, this little Debbie. Okay. Oh, hold on.